In this video, I will give you a high-level overview of the main contributions of our paper on the consistency of kernel methods with dependent observations, which is to be presented at ICML in 2024. The main contribution is a new assumption, weaker than IID, and that is sufficient for the consistency of support vector machines. Let us begin by defining our goal. Consistency is a property that a learning algorithm may have. An algorithm is consistent if the learned function is optimal in the infinitely many data limit. Here, optimal means that it minimizes the risk involving the input-output distribution we want to capture. Importantly, consistency depends not only on the algorithm, but also on the data it is fed. For instance, we cannot hope to learn where we do not sample. The classical assumption for consistency is that the data is generated by the input-output distribution independently. This is the IID case. For instance, Gaussian process regression is consistent under this setting. While there exist works that show consistency under weaker assumptions such as mixing, they typically exclude simple cases where learning is intuitively possible. This is, for instance, the case for some simple dynamical systems where GPA regression performs well despite the dependency in the samples. Capturing such settings is precisely the goal of this work. Specifically, we derive assumptions on the data that enable defining an asymptotic risk and are sufficient for the consistency of SVMs. I will first explain the intuition behind this assumption, which is called empirical weak convergence. Then, I will show important examples that illustrate why it is suitable for dynamical systems. Finally, I will quickly cover the main theorems of the paper, since the purpose of this video is really to convey the idea behind empirical weak convergence. Before starting, I want to emphasize that I will voluntarily ignore some technical details throughout the video in order to keep the focus on intuition. I refer you to the paper if you want to fill in those gaps. Let us first have a look at what enables the convergence of estimators based on IID processes. The idea is then to take this property as the definition of empirical weak convergence. Assume we have f a function and p a distribution. We wish to estimate the expectation of f with respect to p. It is plotted in yellow. A simple idea is to consider the empirical average of evaluations of f at random locations generated by p. This gives us an empirical estimator of the expectation of f. According to the law of large numbers, the estimator converges almost surely to the true value. For conciseness, we now rewrite this condition using the notation that a measure applied to a function corresponds to its expectation with respect to that measure. On the left, we recognize the empirical measure of the process x, which we call eta. Altogether, we get that for all functions f, this convergence occurs almost surely. For this to happen, the empirical measure must, in some way, become a good approximation of the measure p as n grows. In other words, we need to consider the convergence of a sequence of measures. There exist many non-equivalent ways of defining such a convergence. In this work, we focus on weak convergence. We begin by introducing px, the set of measures on x. Then, we say that a sequence of measures Pn converges to a measure P if the sequence of integrals of continuous and bounded functions converge, for any such function. Here, the functions f are called test functions, and Cb is the class of test functions. By changing the class of test functions, we get a different notion of convergence. The bigger the class, the more demanding the corresponding notion is. While the condition for weak convergence is a bit of a mouthful, it is metric, meaning that weak convergence is simply convergence in Px equipped with an appropriate metric. Coming back to our original problem, we see that the empirical measures of IID processes converge weakly to the data generating distribution. This means exactly that expectations of continuous and bounded functions are well approximated by the empirical averages. This condition is precisely what we take for the basis of the definition of empirical weak convergence. After this long motivation, we are finally ready to define EWC. We need to be precise, however, since simply requiring that the sequence of empirical measure converges is not a good definition. Indeed, recall that an empirical measure is random. Therefore, its convergence needs to be stated in probabilistic terms. This leads us to introducing two different notions of EWC, corresponding to whether the convergence is in probability or almost sure. While the resulting definition is perfectly meaningful, it is unnecessarily restrictive. Indeed, the empirical measures form a converging sequence of random elements in the set of measures. However, the current definition only allows convergence to a deterministic limit. We can thus generalize it by allowing a random limit measure. This allows the limit distribution P to also depend on the outcome. Let's now look at two examples that illustrate the generality of the notion and its relevance for dynamical systems. Consider the deterministic process of the inverse integers, taking values in the interval 0, 1. Clearly, this process converges to 0. It follows that it is also EWC to the Dirac centered in 0. Indeed, if f is a continuous and bounded function, then f of xn converges to f of 0 by continuity. This, in turn, guarantees that the Cesaro average of f of xn also converges to f of 0, which is the definition of EWC. Despite its simplicity, this process already illustrates the generality of the notion. Indeed, consider for instance the indicator function of 0. Clearly, the empirical averages of g are 0, and thus so are their limit. This limit differs from g of 0. Coming back to our discussion on classes of test functions, the sequence eta and x thus does not converge to the Dirac in 0 for notions of convergence that consider g as a test function. Without getting too much into details on the related work here, this is precisely the kind of convergence that is considered in some previous approaches. Part of our contribution thus lies in showing that considering continuous and bounded functions is enough for consistency of SVMs. Let us move on to a more interesting example involving a dynamical system, and finally illustrate why we bothered to allow random limit measures in the definition of empirical weak convergence. We consider once again the interval 0, 1, on which we define the following random walk. We begin in 1/2 and move by a length of 1/3 to the right or to the left with equal probability. In the next step, we repeat this except that the step size is divided by 3. We iterate this procedure, dividing the step size every time. Another way of visualizing this process is a ball at the top of a one-dimensional hill, falling on either side with equal probability. The bottom of the hill is the top of another one, and the process continues. This is an abstraction of a dynamical system taking an irreversible step at each time. In more technical terms, this Markov chain is reducible and has multiple reachable, non-communicating classes. Formally, the process writes as follows, where R is the Rademacher distribution. It can be shown that this process converges almost surely to a random variable z. By arguments similar as those for the previous example, x is EWC with random limit measure the Dirac centered at z. An important takeaway is that EWC allows processes to take irreversible steps, which are accounted for by the randomness of the limit measure. This is in sharp contrast with previous approaches, such as those based on mixing, which require irreducible chains. Intuitively, EWC processes are thus those that concentrate somewhere, where the somewhere may itself be random. At this point, it is worth asking whether the definition is not too general, and whether there even exists processes that are not EWC. A simple counterexample is the following. It flips its value between 0 and 1, waiting exponentially longer after each flip. The exponential waiting times result in an oscillation of empirical averages between f of 0 and f of 1, showing that the process is not EWC. The main results of the paper are based on a key property of EWC processes that we now illustrate. By definition, EWC processes are those whose empirical measures converge weakly. This means that the empirical expectations of continuous and bounded real functions converge to their population value. A meaningful question is whether the set of real numbers plays a special role here. In particular, can we replace it with an arbitrary Hilbert space? Do Hilbert space-valued empirical averages of EWC processes converge? Under mild technical assumptions, they do. Specifically, assume the following. X is EWC almost surely, the input space is sufficiently regular, H is separable, and the class of test functions is separable. Then, with probability 1, the empirical averages of all test functions converge. A similar result holds for EWC in probability, but is slightly more technical to state. I'll refer you to the paper for details. With this, we can state the main theorems of the paper. The first one concerns the usual estimator of kernel mean embeddings. Under the EWC assumption, the estimator is statistically consistent. While a weaker version of this theorem follows from the previous key property, this result does not require a separable RWTH in its full generality. The second result concerns the consistency of SVMs. To state it, let us introduce some notation. We consider an input set X and a sufficiently regular output set Y, which is a subset of a separable Hilbert space G. We also consider an RWTH H of G-valued functions, and a dataset Z of input-output pairs. This setup extends the classical one of statistical learning, which only considers scalar outputs. Our main result guarantees that SVMs are consistent for AWC data under the usual assumptions as long as two additional assumptions are satisfied. Namely, we impose a continuously differentiable loss and a separable set of continuous and bounded functions from x times y to g. The first assumption comes directly from the fact that we only assume weak convergence. In the proof, the function involved is the gradient of the loss, which then needs to be continuous and bounded. In other words, the great generality on the process comes at the price of additional assumptions on the loss, and stronger notions of convergence should enable alleviating this assumption. The second assumption comes from the fact that the set of test functions in the key property should be separable. A sufficient condition for this assumption is that x and y are compact. Summarizing, the main contributions of our work are the following. We introduce empirical weak convergence, an assumption that is suitable for data sampled from dynamical systems. We show the key property that Hilbert space-valued empirical averages of continuous and bounded functions converge under AWC. This enables showing that both KMEs and SVMs are consistent under AWC under some technical conditions for the latter. Furthermore, we adapted a general setup of Hilbert-valued outputs, which is of particular interest for some applications of SVMs, such as conditional kernel mean embeddings. Altogether, our results enable showing consistency for kernel methods when data is sampled from a large class of dynamical systems. Our explorations indicate multiple promising avenues for future work. The first question is whether one can alleviate the separability assumption on the set of continuous and bounded functions. A second one is whether one can derive notions stronger than AWC by considering stronger notions of convergence. Finally, our theory only concerns asymptotic behavior and disregards questions of convergence speed. It would be particularly interesting to generalize oracle inequalities, which are an established tool to obtain learning rates, to the case of AWC data. This concludes this video. If you are interested in more details, here is a link to the full paper. Also, don't hesitate to stop by our poster or to drop me an email if you wish to discuss.